Today we are going to see the next class of automata, namely pushdown automata. So before we see what a pushdown automaton is, let us recollect the basic working of a finite state automaton. So what is a finite state automaton? Structurally, a finite state automaton contains a input tape of finite length, a control unit with a finite number of states, and a read head. And what it can do is it can read the input symbol that the read head is pointing to. Now it is small a. Then what it can do? Based on the current state, which is S, and the current input symbol, which is A, it can change its state according to a transition function. So this transition function tells if you are in the state small s and if you are reading this input symbol small a, then you change your state from S to P. That is what this transition function is telling. And after changing its state, it should move its read head one position to the right in the input tape. So if you execute this move or transition in the automaton, then you will get this state where the state is changed from S to P, and the read head is positioned to the next symbol, and that's it. And when an input like this is said to be accepted, input here is ABB, ABAB. When is this accepted? When the computation of the automaton for the input X terminates in a final state. That means if the machine comes to this configuration, that is the input is consumed completely and the automaton is in a final state, then the input is accepted. So that is a finite state automaton. It has got a input tape with finite length, a control unit with finitely many states, and a read head pointing to one of the cells in the input tape. And it, at any point of time during the computation of the finite state automata, it looks at the current input symbol and the current state, and based on these two it makes a transition. Transition means a state change, and that's what a finite state automaton is. And we saw that a finite state automaton is in limited power for accepting languages. For example, we saw that the language a raised to n, b raised to n, where n is greater than or equal to 0, or the set of palindrome words, or set of all words with equal number of a's and b's. All these languages are non-regular or cannot be recognized by a finite state automaton. And the basic problem with the finite state automaton in recognizing these languages is its limitation in remembering information about the input. It cannot count the number of symbols, basically because it's not having a memory or intermediate storage to remember information about the string processed. But it has ability to remember a finite amount of information about the input string read so far as the context of the finite number of states in the control unit. Now the question is, can we add a memory to the finite state automata to get a more powerful machine? And can be obtained in machine which can accept context-free languages. And that is the topic for today. And we are going to learn about push-down automata. And a push-down automata is structurally this. So if you look at this, this is very similar to what we learned in finite state automata with this additional component. Structurally, this is the only additional component that we are adding. That is an intermediate storage, which is a stack. So when compared to a finite state automaton, in a push-down automata, we are adding an intermediate storage, which is a stack. So what would be a step in the computation of push-down automata? We can see. So in this case, it has to read the current input symbol, which is small a here, and the current symbol on the top of stack, and which is capital X. So it needs to make a move based on the current state, which is small s, the current input symbol small a, and the current symbol on the top of stack, which is capital X. And based on these three, what it can do is it can change the state. So now the state is changed to P from S and replace the symbol of on the top of the stack with a string of stack symbols. That is what it can do. It can change the state, in this case from S to P, and it can replace the top of the stack symbol with a string of symbols on the stack. Not that here the input symbols, that is the input alphabet, and the stack alphabet are different. In this example, there are two alphabets shown on the stack. They are this bottom symbol and capital X, and here the input symbols are small a and small b. And after changing the state and replacing the top of the stack symbol with a string of stack symbols as defined by a transition, it has to reposition its read head one position to the right. Same as what we did for a finite state automaton, the read head must be positioned to the next symbol. So if you apply now this transition, this is what is applicable. You are in state small s, and the input symbol is small a, and the top of stack symbol is capital X, that is SAX. From the state S, you are reading the input symbol small a, and you have capital X as the top of the stack symbol. Then what you do? You change the state of the automaton from small s to small p, and you replace the top of the stack symbol with a string of stack symbols y1, y2, etc., yk. This is what we are going to get. So the read head is positioned to the next symbol, state is changed from S to P, and the top of stack symbol X is taken out, and a new string is pushed onto the stack. And what is it? Y1, y2, etc., yk. And remember, yk is going to the bottom of the stack. So it's just like pushing the string into the bucket. So if you want to remember, you can remember it like that. So that's what you can do in a push down automata. And that's what a push down automaton is. The only extra thing that you have in the structure of the finite state automaton, you added an intermediate storage, which is a stack. And so the transition depends on the current state, the current input symbol, and the current symbol on the top of the stack. And what are the components defining a transition? The new state and the new string, which is going to replace a single symbol on the top of the stack. So remember, a single symbol, which is the top of stack symbol, is going to be replaced with a string of stack symbols. This string can be a string of 0 or more symbols. 0 means here you will get epsilon. 1 means if you are replacing capital X with Y, you can say Y. In general, you can replace it with a string of stack symbols. Hope you followed it. It's a very simple concept, and move on to the next slide. So where I'm trying to introduce the acceptance criteria for pushdown automata. There are two acceptance criteria, and the first one is this. That is, if you start processing in this configuration means you are in the start state, the read head is pointing to the first symbol in the input, and now the stack is containing only the bottom of the stack symbol. This is a special symbol to designate the bottom of the stack. So when you are computing, you will be adding elements above it. So this is the bottom of the stack symbol, which is a special symbol on the stack. So this is the initial state for any pushdown automata. The read head pointing to the first input symbol. Start state is the state to begin with, and the stack content will be this for any input and for any pushdown automaton. That is only bottom of the stack symbol. And you accept in this case, when you finish reading the input, the stack is empty, and that is the case. That means the criterion is input is consumed and the stack is empty, and that is the acceptance criteria A, which is what is called empty stack acceptance. That is, you consumed the input completely and the stack is empty. You are not looking at whether the state is final or not. It could be any state. So if you start from this configuration, if you end up like this, that is, you finish processing your input, and when you finish processing the input, the stack is empty. The bottom of the stack symbol is also taken out. Then you accept. That is acceptance criteria A. Then acceptance criterion B. So this is the same initial configuration, and the final is this. So in this case, when you finish reading your input, just like in the case of a finite state automaton, based on whether you are in a finite state or not, you are accepting. If you are in a finite state, you accept, otherwise you reject. In this case, we are not caring about the content of the stack when the machine finishes reading the input. So this is the second criterion. Input is consumed and the pushdown automaton is in a finite state, and this is what is called finite state acceptance. So remember, there are two acceptance conditions. The first one is when you finish reading the input, the stack is empty. You are not caring about the state, and that is called empty stack acceptance. And the second one is when you finish processing your input, if the machine is in a finite state, then you accept. In that case, you are not caring about the content of the stack when you finish reading the input. So these are the two acceptance criteria for pushdown automata. We can take any one, and later we will prove that both are equal. So now we can proceed and see an example pushdown automata before we formally define it. So can we design a pushdown automaton for the language a to the power n, b to the power n, where n is any natural number? So here is an example input given, which is a raised to 3, b raised to 3. We know that this is a string in the language, so we need to accept. And suppose we are going to accept by emptying the stack. So what would be the final configuration? It will look like this. When you finish reading the input, you will be in a state. It may not be yes, you could be in any state, and you finish the stack. So stack is empty. Then by the first acceptance criterion, you can say that this is accepted. So how will you do this? That is, empty the stack when finished reading the input if and only if the input is in the language. The question is, how can we do it? Any idea? So here is a rough idea. If you start with this configuration where you have AQ, BQ as input, and suppose I do this. When I finish the A part, after I finish reading a cube, I will remember the number of A's in the stack by pushing a capital X for each A. If there are n A's, when I come to this position, I'll be remembering n by pushing n simples onto the stack. So number of X will be same as number of A's. So that you can do. Then the stack will tell you how many B's now you need. So then from here what I will do is, for each B I will take out a simple from the stack. And so I will gradually take out all the 3 and I will move on to this situation. Finally I can now take out the bottom simple and I can accept. So that is one logic. You can do it in a different way, of course, but this is a naive or straightforward way of doing it. So what I did here is, I decided to remember the number of A's in the stack. How? I'm not going to count it, but I'm going to push as many X's as the number of A's here. So in this case it's 3, so I'll be having 3 X's on this stack. Then for each B I'll take out 1, and finally if I finish reading, suppose I have only the bottom of the stack simple, I will take out that and I will read this situation without consuming an input. I will take out that. So we can see what we can do like that. So this is the abstract logic for doing it. Now we can see how can we design the transition function. So here is the initial configuration. And what is the configuration? You are in the state S, your input symbol is small a, and the top of the stack symbol is bottom. So what do? You know that above the bottom symbol, for every A, I want to push a capital X. So what will be the right side? I don't want to change the state because I just want to count the number of A's by remembering the number of A's as number of X's here. So what I do is, I'll do this. I will not change my state. What I do is, I will keep the, I want to keep the bottom there, and I want to get a capital X on the top of bottom. So what should I do? I know that by the semantics of Pushdown Automata, at every move I will be taking out the top of the stack symbol. I will be popping it out. So if I want to have it back, what I should do? I will push this string, first bottom, then capital X. So that's what I do. And if you execute now this transition, what will happen? In one step, the read head is moving to the right position and you are getting this as the stack content. And now what is the configuration now? What is it? It is SAX. Now it's not SA bottom, it is SAX, and it is not defined. So what will be the RHS of this transition function? It's not at all difficult. So you may not be changing your state. What I should do is take out this X, and in fact what should I do is, I should get one more X above this capital X. I know that I am going to replace this. So after that I should get 2 X's, and that is why I am doing XX. So I will take out capital X because that is the semantics of the pushdown automaton. And after that I know that I need 2 X's in the top of bottom because already there was an A, one more A. So that is what I do here. And now what the configuration is exactly SAX. So we have a transition already. So what will happen? This X will be taken out and 2 X's will come. Okay, what is now SAX again? So the third step, what will happen is you will move to this B and 1 X will come on top of X because this transition is applied. Yeah, now you're getting a new configuration. S is the state, B is the next input symbol, and capital X on the top of the stack. So here what we decided to do, B is the input and X is the top of the stack, means we finished reading the A part and this is the first B. So what you do, you can cancel the occurrence of this B with the last A. So you can just take out the capital X, and this is how you can do it. Okay, you take out X and push nothing. That is exactly what you want to do. So if you apply, and why I am changing the state is because from now onwards I don't want to process any more A's. If you are in small s, you are going to process A from now onwards also. I don't want to do it. And that's why I changed my state from small s to small p. So if you apply, S is changed to P, and here was the read head, now it is pointing to the next simple, and X is taken out. So what is the situation now? PBX. PBX is not there. So now you have to define a transition for PBX. So what is it? You don't want to change state. You just take out X. So this is exactly P. And if you apply that, what will happen in two steps? This X will also be coming out, and you are moving to the last simple. And now again PBX, so the PBX transition is already defined, you will take out this X. So you finish reading, and now you are in this configuration. What is it? PB bottom. So, sorry, not B, sorry, I don't have any input. So what I can have is, I can have a transition without consuming any input. That is, the next input is nothing, but bottom is on the top of the stack. What do you want to do? You want to take it out. So what you do? P and epsilon. You're going to take it out. If you do this, you will get into this situation, and in this case you are done, because you started with AQ, BQ, and you consumed your input and you emptied your stack. You accept. So are we done? No, we are not done, because how can you accept the input string epsilon? This is the case where you don't have any A's and B's. So this will be the configuration. This will be the configuration. S is the state, nothing is there on the input tape, and bottom is there on the top of the stack. And you know that you have to take out this for Pushdown Automata to accept this input string, that is epsilon. So what you do? You just take out that bottom of the stack simple, and if you do that from this configuration in one step, you will empty the stack without consuming any input, and hence you can accept epsilon as well. And here is the Pushdown automaton for the language, and here is it. I just copied it. This is what we obtained. And as a homework exercise, you try to see how the computation or execution happens for each of these four inputs. Please try to understand the computation of the Pushdown automaton with all these four inputs for you to understand what exactly is happening. And now with this example, we can try to formalize the definition of Pushdown automaton. So recall this example and try to define it. A Pushdown automaton is a structure of the form capital A is a 8-tuple where Q is the finite set of states. In this particular case, only small s and small p are there. Finite set of states. Then sigma is the finite set of input alphabets. Here only small a and small b. And then is gamma. What is it? It is a finite set of stack alphabets. In this case, there are only two, which is bottom and capital X, and bottom is going to be always there, and small s is a state which is known as the start state. And now the transition relation, it's a finite subset of this. Maybe I will explain why this structure. So what is the transition? It depends on the current state, that is the current state, then the current input simple. You know that epsilon transitions are possible, for it is either the current input simple or epsilon, and it also depends on the top of stack simple, that is the stack simple is this third argument. So there are three arguments for this, and what is the outcome? The new state and a string of stack alphabet. So this is okay, and this is not a function. I am defining it as a relation. Because why is it a relation is because of this. You see that if you are in a configuration where the current state is small s and the current input symbol is small a and the current top of the stack symbol is bottom, then you can apply any one of these two transitions. Because without consuming this input symbol, you can apply this. That's always allowed, just like in the case of an n of a. So this is not a function. In this case, there are two possibilities. So that is why I define it as a relation. And why is it a finite relation? I said it's a finite subset of this. A relation from this domain to this range, but it's a finite. Why? Because you know that in the range, the second component is gamma star, which can be any string of stack alphabet, and there could be infinitely many strings. So in that case, it is possible for you to get infinite number of relations like this. But in every automaton, we will only consider a finite number of transitions in our case. So this is just a mathematical representation of each of these. It's a relation from the Cartesian product of three sets. What is your current state? What is your current input symbol? Or without even taking an input symbol, you can make a move. And what is the top of the stack symbol? Then you are defining what is the next state and what is the string that you are going to push onto the stack after taking out the top of the stack symbol. And that's it. And the next component is bottom, which is a stack symbol, which is the bottom of stack symbol. And finally, capital F, which is a subset of states, is the set of finite states. Recall that there are two acceptance conditions. Acceptance by emptying the stack. In that case, you don't need this component. And the other acceptance criteria is acceptance by entering a finite state. In that case, you need this. So this is the definition. And with this, we can move forward and see one more example. So can we have a pushdown automaton for the language of strings with equal number of A's and B's? And you can have it, and here is one. So this is for accepting the null string. In the null string, 0 number of A's, 0 number of B's, so I have to accept. So originally you are in the start state without consuming an input. I am taking out the bottom of stack symbol and entering a finite state. Okay, I am going to define an automaton which accepts by entering a finite state small f. And now, suppose when I have bottom symbol as the top of the stack symbol, I am getting an A. That means I am getting an A. So I need to remember that A. I am remembering it by pushing a capital X on the stack. That's what I do. Next, suppose I get an A when capital X is already on the top of the stack. That means already there was an A, one more A. So what do you do? XX. Now this is another case where I am on the same state as, but I am getting an input symbol small b while I have capital X as the top of the stack symbol. That means capital X is representing an input symbol small a. Now I am getting a b. So now I can decide to take out that X. I am cancelling this occurrence of b with a previous occurrence of a. So that is all what I am doing. And that's okay because corresponding to this b, I had an a. So I took out that. And that's exactly what I want to do. So previously, suppose I already processed 3 A's. And now 1B means I can take out that capital X. 2 more A's I want to see. And that's what. And similarly, suppose initially I am getting a small b. Then to remember that I got a b, I will be pushing capital Y. Then another situation is already I have Y on the top of the stack. I am getting one more b. It's YY. And similar to here, suppose I am getting a small a while I have capital Y on the top of the stack. That means previous symbol was small b and now it is a. I can cancel these two. So just take out this capital Y. And this is what I do, and you can see, verify that this is the correct design. If you want, you can prove it using the principle of mathematical induction, but you at least try to understand it by simulating the computation of this machine on these three input strings. These two will be accepted and this will be rejected according to the number of A's and B's. Please do it as a homework exercise. So we have seen two example pushdown automaton, and one by finite state acceptance, that is this case, and the other one by empty stack acceptance. And with this, we are moving on to the last slide where I am giving you a number of practice questions for you to understand how you can design a pushdown automaton. And these are the three languages, and all the three are proved to be context-free languages because we had context-free grammars. Now I am asking you to find pushdown automaton for each of these languages, and you can decide whether you want to accept by emptying your stack or by entering a finite state. It's up to you. Okay, which one is easy for you? You take that acceptance criteria and you design a machine. So today we have seen pushdown automaton, which is obtained from a finite state automata by adding a structural component, which is a stack. So in this case, the move or transition is based on the current input symbol, the current state, and the current symbol on the top of stack. And the transition defines the next state and the string of stack symbols, which is going to replace the top of stack symbol. And remember, always you have to take out the top of the stack symbol and you have to push a string of stack symbols. So please try to design pushdown automata for all the three languages given, and also try to understand how the example automata works by simulating its computation or execution on the input strings given as homework exercise. Thank you.